Thank you, everyone, and good afternoon. Thank you for attending session 2 of the Pennsylvania Sea Grant Bluff webinar series. For those that attended the first one, welcome back. For newcomers, thank you for joining us today. Just a couple notes since the first webinar, a few folks had reached out to me interested in continuing education units. And so I did have the opportunity to reach out to Penn State Community Workforce Programs, and they are able to offer CEUs for this webinar series. They're in the process of setting it up in their system, so they will be sending me a registration link. So if anybody's interested in receiving CEUs, please send me an email and I will get that registration link out to you. The caveat is you will be required to attend 3 of the 4 webinars to receive the CEUs through this program. Also, today's webinar is being recorded and we will be posting it on the Sea Grant website once it's available. Webinar 1 was also recorded and that is now available on the Pennsylvania Sea Grant website. So again, welcome. My name is Sean Rafferty. I'm the research director with the Pennsylvania Sea Grant College program, and I will be facilitating today's webinar. And really the purpose of this series is to highlight recent research and extension efforts conducted by both Penn State Behrend faculty and Sea Grant staff aimed at improving our understanding of bluff recession along the Pennsylvania Lake Erie coast. I'd like to specifically thank our sponsors. So the Pennsylvania Department of Environmental Protection through the Growing Greener program provided the funding for the project, and the information we'll be presenting today as well as in some of the other webinars. Also like to thank Tim Bruno, our program officer with DEP. He's the Chief Office of the Great Lakes. Thank you for his patience in this project, and we're excited to be able to present today. Before I turn it over to Dr. Naber, our presenter today, just a couple housekeeping notes. Again, this webinar is being recorded and will be available on our website. And also during the webinar, if you have any questions, please use the Q&A feature through Zoom to ask any questions. And what we'll do is we'll hold the questions until the end. And then at that time, we'll address some of those questions and answers. Mike and myself will do the best we can to answer those. So again, thank you for attending today's webinar. We're excited to be presenting this project. And so without further ado, I'd like to turn it over to my friend and colleague, Dr. Mike Naber with Penn State Behrend. Mike, the virtual floor is yours. I will stop sharing my screen and hope there's no gremlins and you can share your screen.
Great. Thank you very much, Sean. Hello, everyone. My name is Michael Naber. I'm an assistant teaching professor of geosciences at Penn State Behrend. I teach there with Dr. Tony Foyle, and I've been working quite a while with Dr. Rafferty and Dr. Foyle on this project, and I think we have some interesting things to show you today. As the title says, we are looking at the bluff recession along our property here in Pennsylvania from Ohio all the way to New York and such, and we're looking at possibly some new methods using geospatial data to look at this, hopefully to make things a bit more efficient and effective in gauging what is going on out there. So presentation today, just a little outline. I'm going to talk about the background, talk about the study area, the Lake Erie coastline, talk about bluff recession along this about 77-mile corridor that we have here of it. We're going to also look at the formal process that is done by PA CRM and kind of talk about the motivation behind our study in general, and then of course the big tool that the USGS puts out, DISAS. Talk about the methodology a little bit, where we got our data, what the data looked like, some of the accuracy of it, then talk about some of the specifics of running DISAS and interpreting those results. And then, of course, the meat of the study, the results and some of the more interesting findings from our study here, and some comparison between our study and the PA CRM study. And then at the end, of course, we'll have some advantages and some limitations that we found going through this study, and then where we're going to go with it next. So a little bit of background, if you're not familiar, from the border of Ohio to New York, we have around 76.6 miles of shoreline, or 123 kilometers. We call it formally, the geologic name for it, the Central Lowlands Province. Obviously quite a bit of glacial activity through this area through the last ice ages and such, and they've left some interesting things behind and have done some interesting things on their move through here as well. Eastern and western reaches of this, you can see up here on the map that we have our eastern side over here, and then our western, and then of course the core area here in the center is where Presque Isle and the city of Erie proper is. Our bluffs range from around 5 foot high to somewhere around 180 feet in elevation. So there's a good bit of variation in there. There's also some areas in there where we have bedrock exposed, and then we just have unconsolidated sediments and such that form it in other areas. And then of course, this area has been considered or designated a BRHA, or a bluff recession hazard area. In the county itself, we have somewhere between 220, 230,000 people. And in the city proper area, we have around 110,000 people, and a good amount of them live in a very short distance to the lake itself. And this is kind of, it's not something new, right? Around 86% of the planet's population lives within, say, 2 miles of a water feature, whether it's a lake, the ocean, a sea, or a river body and such. So when things happen close to that, there's the possibility of damage to these facilities and such by natural processes and such. In this area, we have around 70 different watersheds. Some of them are quite large. Quite a few of them are rather small. Elk Creek, Walnut Creek, probably being two of the bigger ones that are known by a lot of people, even outside of our area, because of what the trout and such do when they're running up those streams. We also have 9 different municipalities in this area, from Springfield in the west all the way over to northeast where the New York border is. And of course, including the city of Erie in there in the center. So a definition of bluff recession: proper loss of material along the bluff face caused by direct or indirect action by one of a combination of opportunity or events. They can be groundwater seepage, of course, water making its way to groundwater making its way to the lake or down elevation and such, has some different and interesting effects upon it. Water currents themselves, so longshore current mostly comes from the west, but we can also have a shift in wind, and we have an east shore current that sometimes occurs along the lake. Of course, that's mostly dealing with prevailing winds and such. Also, wind generated water waves. When we have large storms and such on Lake Erie, when the direction is correct and coming, say, from Canada, we can have some rather large breakers, somewhere between 20 and 30 foot, quite substantial. And then, of course, in recent history, we've kind of had our historic high water levels and such. And of course, that puts new areas into the erosional equation, working on the toes of the bluffs and such. It is good to remember recession is part of the natural process. It happens naturally. If we weren't here, if humans weren't in the equation, we would still have recession here in Lake Erie, but elsewhere around the world where we have bluffs. The things here that we're quite concerned about, though, is kind of the human influence. Are we exacerbating, the conditions that are happening by what we're doing with our activities, whether it's a marina or a dock, or say somebody putting in a groin and such. So coastal developments in there. Also, the idea of what do we do with wastewater, or also stormwater runoff. We know we can do things correctly, but we also know what happens, or can see what happens very easily when water is directed there, and that power of that water really starts to work on the bluff face itself. So humans have an effort there, but also unsustainable land development practices. A lot of people that have bluff or live on the bluff really like to see the lake itself. And sometimes to do that, they do things that are not really sustainable, and not good for their bluff line as well. So removing vegetation, cutting down trees and things that might interrupt that view and such, exacerbate the process and sometimes speed up the process of erosion in those areas. Just to mention down on the bottom there, Dr. Foyle and Dr. Rafferty had an SOK report kind of looking at the status of things that are going on in our area, but also other things that we are seeing elsewhere around the United States in general, where we have bluff line and such. So, places in on the other Great Lakes, places in Alaska, Washington, Oregon, California, and then of course the Northeast have quite a few areas that deal with it with their Atlantic frontage as well. So we're not the only ones with bluff, and of course we can learn a lot from those other places, from what's worked and what hasn't worked so well there. So a little background, kind of giving us the understanding of the motivation of our study here. Pennsylvania Coastal Resources Management Program, or the PA CRM, they have been monitoring the bluff and bluff recession using control points, around 130 of these from the Ohio border, usually around 500 meters spread on average from Ohio all the way through the city, and then to New York on the other side. That gives them around 130 points. So their retreat rates that they've seen since they've been doing this, and I think it's been since 1982 and such, is what they've seen with these 130 control points is an average of around a half a foot a year, or 0.15 metric in a year as well. So our question, one of our big questions kind of leading us into the study, is this enough? Is a 500 meter interval enough to capture enough variation so we have a good idea about what the true average is? Other issues that have come to the front on this as well, when they do this study, they look for a piece of metal in the ground using a metal detector. They have a good idea where it's at and such, and then they come out and they shoot an azimuth, or they have shot an azimuth towards the lake itself. Now, one of the things that it's come to mention that hasn't been taken into context with this study at all is the idea of polar wonder. And if you're paying attention to the news, our pole is moving quite quickly towards Russia at this point. And maybe there's a reversal kind of coming, but that's another class in general on there. But never taking that into mind, we've from 1982 to 2021, we've had a shift of around 2 degrees and a half minute in that movement of that polar wonder, and it was never actually factored into the equation and such. So are we truly measuring from year to year with that study done by CRM what we truly think we are? So that's another possible thing that we've been thinking about. So as I was saying, we have an understanding that there's quite a few people that live here in Erie County. I know it's nothing compared to Pittsburgh or to Philadelphia, but a couple 100,000 people live here, and a good amount of them, or a good percentage of them, live in very close proximity to the lake itself. And there is also quite a bit of infrastructure and industry that lives in close proximity to there. So around 265 buildings and properties are currently kind of in a risk zone, somewhere around 66 million. That was in 2012 dollars. So obviously that number probably might be quite a bit higher now as the city has grown a little bit, but also a bit of inflation and such. In 2012, Dr. Foyle and myself did a pilot study just looking at, say, a 6-kilometer spread, and then manually digitizing ourselves the crest lines with the use of aerial photos, and then DEMs derived from LiDAR data that the state had run through different agencies and such. And we found some interesting things. And we also found that that method of manually doing it is quite laborious in its nature and a bit subjective. So we were wondering if there were ways to automate this effort instead of doing it manually by hand. Maybe technology had come to the point where we could request with that LiDAR data, and with the use of that LiDAR data, kind of look at how true that information is to what we see on the ground and such. So if you're not familiar with LiDAR, that's just a sensor on an airplane or on a drone that goes over an area, and with the return signal back towards the machine, whether it's a drone or a plane, it's recording when that hits the ground or hits vegetation and such. And we can use certain returns to gather what the ground data was versus what, say, vegetation or some other things that are above it would record and such. We also wanted to do a look at what other data is available, and if the data that we use, say back with the 2012 study from 1998 or the 2007, if that would be useful to look at and use with current data that has been run since then as well. So also we started to look around and to see if there were tools that might be available out there for us to use and to do this automation instead of this manual kind of delineation and such. And we found some good things, of course. The United States Geological Study Survey has a nice tool out there. Of course, the tool was invented to look at shoreline and shoreline retreat and movement in different places, but it seemed to have the right things for us. One, it was free, and it is kind of maintained and monitored, and newly released versions of it are put out with pretty good literature and such. One, it did or has the capability of doing what we want, even though its intended purpose was to look at shoreline. Obviously, a little bit of difference between shoreline and between a crest line, but still linear objects that might be able to be gathered by the use of this, and also have some interesting numbers put out by it. So what does it do exactly? You create yourself a foreshore or a inshore kind of baseline, and from that at a 90-degree angle, it goes through, or its intended purpose was to go through shorelines, historical shorelines, but also currently derived shorelines, and allow the user to understand what types of changes, whether recessions or gains in areas, and allows you to make some interesting clips in an automated manner as well, giving you an understanding of what those differences between timeframes and such are as well. So yeah, it does a lot of things nicely that we possibly could use with crest lines. And also it has, like I said, some of those neat characteristics. Most agencies that Dr. Foyle, myself, and Dr. Rafferty work with have access to ArcGIS, but have the access as well to this free app through the United States Geological Survey and such. So it has recently also been used in bluff analysis in some places. One of those places was in 2014 in Island County, Washington. Another study was done on Barter Island in Alaska, and then quite recently an area in Wisconsin where a university had done some changes to the bluff line to kind of hopefully control the recession that was happening in there. And then they did a short kind of study in that area to see what it looked like in a few years and what it looked like to pass not shores, but crest lines in that area. And there are a couple others out there and such, but looking for ones with just pure publications and such out here. These three are quite good and quite current as well. On the right here, you can kind of see that idea of a baseline and then the automated transects, and those transects and that distance between transects is totally controlled by the user. So the GIS user is the one that gets to dictate how these transects are separated, what they are looking for. Are they looking for a closer to the shore kind of object or crest line, or are they looking for something further interior and such? So it does give a good amount of control to the GIS user. And there's quite a bit of statistics and such that can be also gathered through this, but that is for another study that we'll not really get into today and such. But there's some neat information that can be used, especially when we have not just 1 year or 2 years, but multiple years to look at in kind of a temporal manner. So yeah, it really seems to be able to do, or seem to be able to do, what we wanted it to do, even though its intended purpose was with shorelines and such. So that begged the question of what type of data do we need? And since DCNR and PADP and other agencies had already been under contract with different groups to gather LiDAR data. There was some data that had already been created. And then, of course, we wanted more current data. So running the information on 2015 or gathering information or processing that information was done as well. We found that 1998 data did not have enough strikes or points that were generated for the peculiarities of what we were needing, but the 2007 data that had already been run definitely did have the point ratio per square meter that would be necessary to do what we want. The 2012, of course, showed that wonderful characteristic of LiDAR data, getting better, getting more points per square meter on the ground, and also running with different types of units that are, or sensors that are more capable. And then, of course, 2015, even having better point density on the ground and even better resolution and such with it. So we found 3 good years of data. One we had to have run by Wolpert, and then Wolpert did run the 2012, and then the data from 2007 had been already run by another state agency. So that nicely played into our pockets of only having to have it run for the 2015. We thought this was a pretty good advantage to us because that 2007 to 2015 gave us a long-term look at some changes, but that 2012 to 2015 gave us also in the mix a look at what would happen or what we could gauge on a short-term basis, so, of a 3-year period and such. We assessed information and gathered rates by watershed. Like I said, there's 70 different watersheds in our region. So taking that data and agglomerating it to the watershed, and also gathering it and agglomerating it to municipality was quite possible as well. So giving some useful information on HUCs that have already been satisfied or created, but also being hopefully able to give municipality information, allowing them to understand what's going on within their public entity as well. In the process right now by Dr. Foyle, Dr. Rafferty, and myself is another thing whereby we're going to hopefully look to the future and see if we can use data that we have to give us an idea of where we think changes or how much change might happen in the future. We call it in shorthand BEPI, but that's the Bluff Erosion Potential Index. And that'll be talked about by Dr. Foyle, but is, like I said, currently being done, and a little bit still has to be done with that. So again, the big idea there was to use a couple more of the derivations from that LiDAR terrain data that we gathered, and to also look at, say, seeing areas that might actually be at higher risk than others and such. So the ortho imagery, as I said, was run by Wolpert, both in 2012 and 2015, 6-inch resolution at both of those intervals. And maybe if we continue this with the resolution, as it seems to do with a little bit of time, continues to get better. We did collect it in 4 bands, so the RGB and also in infrared and such, to give us an understanding if we wanted it, or other entities to look at vegetation and the health of vegetation in different areas in there. The LiDAR data, like I told you, the 2007 had already been run. That was done with DCNR. And you can kind of see some of these changes and benefits that come over time with technology. So 1 dot every 1.4 meters density there with the 2007. We get to the 2012, and that comes down to 1 meter. And then with the 2015, we're looking at about 0.7 meters, or that 2.3 foot density. So it does continue to get better. And I think if we look to the future and doing this again in the future, that we would probably see some additional betterment when it comes to dot density on the ground, and our even better chance to understand what's beneath us and such. Watershed boundaries were another things that were run by Wolpert. So updating the watersheds in our area was one of the things that they were doing for us as well. So they delineated the current ones that you would see on PASDA and such with that LiDAR data. So there were a couple different things that happened with that data set from Wolpert. So our procedures now. Now, this is proprietary kind of through Woolpert. And of course, they have some software and such, being a remote sensing company that say Penn State and different agencies, of course, in the state of Pennsylvania and other places probably don't have because of the costs and the learning curve according to them, but kind of using some basic terms of things that they used to delineate the bluff line. So it wasn't necessarily somebody going through and placing dots and arcs between those dots. They used the DEM digital terrain model, and they also use some of the derivations from that data as well. So slopes greater than 38 degrees were taken into context. Hillshades kind of give us an idea of what faces the sun and what doesn't, but it also helps you kind of get an idea of what the 3-day scape of the surface is. So it's quite useful there, and it comes in values, and the value of greater than 184 was deemed to be something that would show them, of course, where that crest line might break as well. Some terms like curvature and such could be also gathered. These are quite important when you're looking at hydrology and watershed function and directionality of water moving through an area. And then the profile itself would be looked at. So a profile being kind of a side profile of what we would expect from 3D analysis, which is another app that's available with ArcGIS and such. So taking these three things together, they did what they called a stacking method with eCognition software. Again, it's kind of like adding things together. If you know anything about ArcMap and such, map algebra and such is something where you bring different types of derivations together and such in an object-based image analysis way. And it, with a certain pilot set, the software itself runs through algorithms and continues to learn, say, as it moves through that area. And I guess for me, the simplest way to kind of look at this would be kind of like a principal components analysis, where we're looking at, say, vegetation or landscape, and how the software tries different values and groupings to identify in an unsupervised manner what we would see on the ground and such. And like I said, it continues to learn, just like the PCA. It might put something into a group, and then as it goes through those different iterations, it might remove it and put it into a different group as well as it's going through it. So it kind of learns as it's going through this software, and kind of bases what it finds in some places with other places and such. So it's quite neat. I don't know that it would be automated intelligence or AI, but it pretty darn close, and come up with some pretty interesting results. You can see in this example here in the center, those different derivations that they were using and such. And in almost all of them, we can also see from the sample that Woolpert provided, you can kind of start to see the break of the crest line kind of occurring and such. So using them together in a manner that helped them to automate this idea of delineation was the hope. And at the bottom, you kind of see what they would have had as their final product. Kind of, even though it's a 2D surface here, you can kind of gauge really easily where that break in that bluff crest is. And they did it so well that they ended up doing a published article in one of their remote sensing journals and such. They really liked what they came up with, and I think we really liked what they did. And of course, it also was kind of ground truthed with the aerial photography that they ran, and also with different features on the ground. So ground truthing means going out, say, with the GPS and seeing if say like a telephone pole or an object that doesn't move readily is in that same location, or how far off it is and such. So they definitely did a QA and QC kind of going through it and making sure things were correct from Ohio all the way to New York and such. So definitely it satisfied their standards. And in the end, different people like Mr. Bruno and Mr. Rafferty, myself, and Mr. Foyle, of course, had comment sessions with them and with their technicians as well, and produced some pretty good data, we think, from the 2007 LiDAR data, the 2012, and of course that 2015 data. So just a little bit there if you're concerned with accuracy. Again, I kind of pointed it out before, but just the big thing to focus on here as time goes by, the technology like LiDAR, definitely the sensors seem to be getting better and seem more capable of picking up more and more returns from the ground. And if you don't understand the surface of a bluff face, it's not a flat surface. A flat surface or a relatively flat surface is quite easy to get really good returns on. Here, the obstacle is to deal with a sloped surface. In some cases, even having almost a 90-degree slopes where we have cliffs and such in the region. So the ability to get a good point density on that slope surface that is also covered with vegetation presents a little bit of a challenge and such. But I think with the advantages of the new sensors and the new software that we have out there, we are definitely getting to a point of really nice data when it comes to that bluff face. And of course, that's the thing we're looking at here. You can also see that as time goes by, vertical accuracy definitely seems to be getting as well better. So up and down elevation, and being on point with elevation, going from 0.9 in the 2007 data to 0.08, or wait, 0.59 in the 2015 LiDAR data. And then, of course, down there on the bottom, just that really wonderful number of our point density, 4.59 in 2007, almost having that, and 2.3 feet there with the 2015 data. So again, the main players in this and getting it done were DCNR with the 2007, and then Wolpert has been doing most of the data collection and data delineation and such since that 2012 data. So it's nice to have the same vendor doing things, knowing that the same things that we requested in the other data would be done in the future data. So methods, this is a very simplistic breakdown of it, but if you go on to the USGS websites, you will see the diagram or rubric that's on the right there. The big things to pull out of this that I'm going to mention right now are our inputs. So what had to be created by me? First off, we had to create a baseline. So the baseline is that linear entity from which we shoot our transects from. Our transects are optimally at a 90-degree to that baseline. And to do that, what I used was a buffer, like a 100-foot buffer of our bluff crest line, both in all directions, kind of in a radius around that. As it moves through that, it creates kind of a nice, larger, more smooth entity. Then what I did was I offset that towards, we tried a couple things, and of course that'll come up in limitations and such, but we tried an inshore baseline, and we ended up running with an offshore baseline towards the crest line itself and such, and found that gave us kind of the results that we wanted. So I took that polygon of the bluff crest line buffer, and then I exported it to a line, and then I did some clipping to it. And again, I created a nice feature that was a muted representation also of the bluff crest itself. So that took a little bit of work, of course, getting it to where it was useful and such. On the offshore was quite a bit easier than working with it inshore. The inshore one seemed to really kind of show us some problems. Again, I'll talk about that in limitations. So of course, the bluff crest files were delineated by Wolpert. They did the 2007, the 2012, and the 2015, using the same method on all three of those years of data, and outputting, hopefully with the same accuracy and such, different bluff crest lines, of course, which I brought into ArcGIS, and of course were the basis of this study. So the steps, of course, which are controlled by the technician, are our default parameters. We wanted to see, or one of our biggest motivations behind our study was to see if we could, one, automate what we're doing. So have the computer do the work instead of having the technician or technicians do the work. also have some control over the distances between the transects that were on our line. Now, the study done by PACRM, theirs was a 500-meter distance between their control points. We wanted to see if we could find one that made sense and made things effective and made them efficient. So we came up with around a 20-meter breakdown between our transects from Ohio all the way to New York. So where PACRM had 130, we ended up with somewhere around 2,300 transects that would cross over the crest lines in the areas that were deemed important. So some things were deemed outside of our study area. That would be places like, say, where Elk Creek and Walnut Creek or streams came in, and where, you know, the shoreline, of course, would end at or the crest line would end at a point as it's coming into those water valleys and such. So some things were actually removed from the study because we didn't have a bluff to deal with and such. Of course, that came in the edit part. Another thing I'll talk about in the limitations is the changes between different versions of DISAS. It appears that what we started working with back in 2015, 2016, which would have been DISAS 4.0, had a bit looser tolerances to the type of data and the type of things that we were doing with the data editing and such, say removing transects or putting in transects where we thought maybe an area needed another transects and such. So that caused us a little bit of grief, especially in one sense, we were working on one group of transects for 3 months. And we went to run the calculation and it refused to use it. We asked the people at USGS if they could find problems with it, and they couldn't get things to run with it either. So again, that'll be in the limitations I'll talk about, but it is the reason we went with an offshore versus having an inshore transect and baseline and such. So calculating change statistics is quite simple. It actually works with the press of a button. Either it works or it doesn't. And we found situations where it worked really well. And we also found situations where it didn't work at all. So there was a little bit of trial and error in that method, but it definitely did run, especially when we had it setting offshore and coming inshore and such. So again, outputs that were useful and beneficial were the linear transects and the statistical outputs that they put out. But more importantly, within the DISAS software, we were able to clip those transects between the areas and intersections of our transects and the bluff crest itself. So what it does is it creates a point file where there's an intersection between the transect and crest lines. So it notes those points by placing a point file, a point vector file at each instance of an intersection. Now, when it doesn't find any change in those areas, it does an interesting thing. It produces a null transect and lets you know that, which is kind of useful. We did have areas that over that 8-year period didn't move at all. And then, of course, through that 3-year period, we even had more areas because it's a shorter time frame that didn't move at all. So it allows you to understand pretty easily and pretty well that things did not happen, or there was no changes along those transects as well, by producing null values and such. So that's kind of useful as well. So that's kind of the methods. You can see that over here: default parameters, cast transects, types of things that I just mentioned, whether foreshore or being onshore, editing, do we want to move things and such. And then, of course, the simplicity of once you have your transects and your transects are good according to the software, you can calculate change. And like I said, they use those point files and then allow you to make clips of the timeframes between those crest lines and such, which is really helpful because that gives us our length, which is another output where the software automatically clips to all of those points of change and intersection that are lying on those transects. So some nice stuff. Now I'm going to kind of show you some of that, I hope. If we're looking from the technician's standpoint, and we have some good aerial photos behind us and such, we can easily, once we have run our clips, we can find our areas of change, and we can also find our length of change between those periods as well here. So what we're looking at, or what you're seeing here in the red, is the change between those three crest lines on a location in Fairview, Pennsylvania. So pretty easily, by using the identify tool, which is up here, one of the standard tools of ArcGIS, all you have to do is click on that new clip, and you can see the files, or you can see the information that you have associated with it. Now, of course, this information up here from TCD to EPR-UNC, that's some statistical information, of course, that we'll publish in the future. But the more important thing here is our shape length. And in this case, this is in metric. So this is one of the places that's identified from 1982 to 2015 as having around 80 feet of recession. This place is, in, like I said, in Fairview, Pennsylvania. And of course, we can compare that with that control point data, which I did, but even in the short term, from 2007 to 2015, this area here has had considerable movement. So, you know, this one here, we have 4 meters of movement, so 4 times 3, so 12 feet of movement in that time period. And then we can see some of the other areas in here. Now, the interesting thing that you can't see here is the 3 properties along the bluff from this property that you see right here. All 3 have groins protruding out into Lake Erie, basically starving this location right here of having any of that longshore current transportation of silt, sediments, you know, and rock and matter. So it makes sense why they've had quite a bit of movement and such here. But the easy part, like I said, is kind of cool. You can see some of your information right in the table of context, but you can also identify things. You can see what municipalities they're in. You can see what watershed. This one here is in what we consider to be unnamed Trib 12 or tributary 12 coming into that Fairview area and such. So quite easy to see, and with just a little bit of change in symbology, you know, colors, maybe width of line. And I like to put those intersection points in here. You see it up here, transect 20 meter, intersect 2012 to 2015. So it shows the short term, but it also shows us the long term. In this case, since it's 2008 to 2015, those are the ones we see there, and we should see 3 points along there if there's change. So a really nice interface, a really easy to look at, and easy to make maps or to make screen captures to show audiences. So in the next few slides, I have some information showing you some of the areas that stood out. So areas of large movement from that 2007 to 2015 data, the long-term data. And again, trying to show you how easy using the simple tools that are available through ArcMap to identify kind of what we're working with. In this situation right here, we are looking at a place in Northeast Township. This is probably one of the largest, we call them blowouts in our vernacular, but one of the biggest areas of movement here. So, and that's no joke. That's 26.19 meters of movement in this area here. And again, you can see they have a cabin that's kind of right here on the very cusp of going into this area as well. And then of course, you can see that nice spacing of 20 meters between points. Again, you see it's not completely going through the center of it. We don't want to sit there and change every single one so they get the greatest. In that essence, this is kind of random. It's showing you where the 20-meter break is going through these and such. So it definitely captures some nice information, and honestly, probably over 30 meters of movement if we were to look from that crest line that is new to that area where it was back in 2007. So quite a grandiose change here. Here's another one that's 12 meters in movement, almost 13 meters in movement that we have from the 2007 here. And again, things to point out, that nice 20-meter distance. Again, CRM was looking at 500-meter. So the points here are nicely separated by that 20-meter. And of course, if you think about over the 500-meter points or breaks between the control points, there's quite a few areas that would pop into there or are not being captured here. So again,
hey, Mike, this is Sean. Just jumping in and let you know you have about 10 minutes left.
10 minutes, great. Thanks, Sean. So these are areas that really stand out as you're moving through. So again, the idea and the easy idea is getting these clips from our transects that are easily calculated and tell us what the movement from those crest lines have actually been. Here is kind of a more standard kind of look of what you would see through different habitated areas. And then, of course, here in Harbor Creek, just to show you an example, new house being built, new subdivision kind of over here. You can see with that and the house setback here from the current 2015 crest line, 70 feet. Their neighbor here, if you look at that, I calculated that out to be about 15 meters from the crest line and such. So some things that might be of concern, building a house and having a relatively short setback. And then we thought it would be good to show you what null areas would look like as well. So we see points here for our transects dropping onto places, but in essence, one of the best things you can see here is this is a natural area. The vegetation is left behind and we don't find much movement over that whole period here. We move over to the east here and we see where houses are and we kind of see where people have removed the vegetation and we have a little bit more of movement. Again, over here, just another example from another area closer to the city of Erie. And we can see those nulls, areas where we had no change and then areas where we had just a small amount of change. So moving forward to the results, the meat of the study, we can see here on the left are municipalities, and you can also see by end the amount of transects that we have by each area. Nice numbers, 450, say in Harbor Creek, at least 264. Remember that number in the city of Erie. And then, of course, next to that, you see the outputs and rates in meters a year and also in feet a year, giving us an overall look at the municipality rate there for that long period of 7 to 15 of somewhere between 0.73 feet of movement on average in that long term. Keep going here because I'm running out of time. Just another look at that with the bar graph. Again, we see it seems that Northeast is having some large movements there, and that's identified pretty easily when we look at the rate of change in feet a year, very close to a foot a year here in their area. Moving forward to the short-term data, 2012 to 2015. Again, look at the city of Erie, around 240. Remember, these vacillate by nulls. We only used areas where we had change along those transects. So if there was no change, which null said, then we would have less transects that would come into that study because they said no change. Again, you see that makes sense over the shorter term that we would have probably more areas where we'd have less change. So our number here is a little under 2,000 where the other was 2,300. And then a look at our rate, particularly in feet a year in that short term, we see over a foot of movement there in that time frame. So a little bit of change. And of course, obviously, things aren't mediated out when you're looking over a small amount of time versus, say, over a larger amount of time. And that makes sense. Again, a bar graph showing us exactly our bluff rate change by municipality. And again, the usual subjects are kind of doing things over on the eastern side of the county. Again, Northeast having the highest at around 1.6 feet a year and change. Just a quick look at watersheds. Again, there's 70 of them. The thing I'd like you to focus on is around 2 feet a year. In recession, a few places, again, Godfrey Run is a usual subject. You'll see this again. This is over our longer time frame. And then you have a few that are over 1.5 feet. And then we go with a different look here of that 2012 to 2015 era. And we start to see in that short term some areas. Again, Godfrey Run had quite a bit of movement. And then we have some other players that are kind of coming into the midst there with 2 feet a year and change. Leading us to kind of compare or look at the CRM results. One of the biggest areas we know is the difference of what they are finding in averages in different places. It seems some areas we find a little less movement, and then other areas we identify areas of greater movement. Again, they're at a 500-meter break, we're at a 20-meter break, and it appears that they only have 3 control points within the city of Erie, or that municipality of the city of Erie, where I told you to take note, 238 transects and also around 260 transects were found in that area. So quite a bit more of locations of measurement is what we're looking at, and kind of a little bit of a different picture between us and PACRM. And we see that here with the comparison to CRM's movement, what we see on the right here, and then what we came out with our rates per year 2012 to 2015 of about 1 foot a year on average, and then over here of about 0.7 with their 0.5 foot movement. And even in some areas like Lake City, we had at least 8 transects that went through it. They did not have a control point at all in that municipality and such. So big things to look at are down here, the overall, but also to look at the differences by municipalities between the CRM and between what we found. So a bit of difference there, both in the long term and the short term. So bar graph, just to show you that in a different way. Again, some differences being bigger movement, what they found on the western portion of the county, and then what we found with a lot more transects was actually quite a bit more movement on the eastern side of our county through townships like Northeast and Harbor Creek and Lawrence Park. Our big takeaways or discussion items that we thought were advantages: LiDAR keeps getting better. Every year, the technology keeps getting better and the sensors getting better. One GIS person or technician can do almost all of the analysis once the data has been run from one workstation. Instead of having multiple interns that are changing and having change over a 3-year period, but also permanent work staff that are moving through these positions and probably not working on it the next year. Ground truthing is definitely doing well with the changes of GPS and GPS ability to collect areas and to denote areas of smaller and smaller change. Most wonderful part about it is DISAS is free. It comes with really good documentation, even tutorials and such with dummy data sets to allow you to go through it and see if you're doing things the way they are. The neater aspect, of course, is that we're able to store and keep these crest lines from past years and compare and use them to future years. And of course, having 2,300, say, transects and areas of measurement compared to 130 areas of measurement is quite a difference, and definitely, I think, gives you a more complete view when you're looking at more of those areas. And then, of course, if you wanted to do the purely randomized effort, you could pick different lengths between your transects, or you could start at different start points, and that would randomize it. But we think that the neat thing comes in that we can reuse from period to period transects and look at the measurements that are happening there in a temporal aspect over time. Though, mind you, even if we change where the transects are, we still have the recorded crest lines at those areas. So we still do get an in-depth temporal view as well. Some of the problems, of course, or limitations would be there was a process to the delineation. We don't have the software, nor do we have the background. So there's quite a bit of a learning curve for agencies that don't have access to that, and also cost problems. Learning curve as well is there for ArcGIS. I've been doing this since 2002. If you're having somebody that, say, has only been doing it for a year or two out of college or something, the learning curve might be greater. Data costs, it's not free. The past data definitely is paid for. The future data, of course, costs are getting lower and lower with newer and better technology, but it's still there. Cost is an issue. Aerial photos, one of the things we ran into, Wolpert did not shoot obliquely into the bluff. So some of the aerial photos, you're missing views of those areas because it's actually the obliqueness is out to the lake instead of into the bluff itself. So being specific out front and saying this is what we want, that is one big one. Again, we had some app glitches, we had some problems as this software goes through bigger or newer iterations. It seems it's more stringent. And of course, that led to some big uses of time and problems of working on things that we couldn't use because we edited them and it wouldn't accept it. ArcMap and DISAS do have learning curves. You don't just jump into it and drive it. There's some things you have to figure out. One of the bigger questions we had, of course, was what happens if a vendor changes? You saw that Wolpert ran the last 3. Can another vendor do the stacking method that Wolpert did? That's a big question. Another big question is PA CRM. Are they going to buy into the use of some new technology, something that has a bit more cost to it in the front end, but definitely makes some really neat stuff in the back end or the more current time. Also with the public, this isn't exactly simple software to use. It does have quite a bit of a learning curve, and there's quite a bit of jargon within the ArcGIS community. Is it possible to relay this information to people that have never opened or have even worked with a GIS program themselves? Last on there is one of the neat things I found is I did everything from my desk, and we did our ground truthing at public locations or public property locations. We didn't have to get permission. We didn't have to go onto somebody's property with a metal detector and such to find things. So that was really kind of nice to not have to deal with maybe a public that doesn't want us there, or it can't be there, or won't allow us there without them being there and such. So that to me was kind of neat to be able to do almost everything from my desk. In the future, of course, I said this is preliminary data. We're going to fine tune it, clean it up, and of course, do our job reporting to PADP, but also we have a hope of publishing this material to maybe a refereed journal that is out there. In the end here, the BEPI or the BEPI Bluff Erosion Potential Index is kind of the next step where we take these derivations that we've done in delineations and such and try and predict areas that will have problems. Kind of apologize for using up all the time. I hope there's a few questions that are left. I think one of the big things we have to understand is it's a wonderful resource. We're loving it. Are we loving it to death? Are we doing the things correctly, or the things that we should be doing correctly along such a wonderful resource? So with that, are there any questions from anyone?
Hi, Mike. I'm going to jump back in here. Yeah, we did have a few questions. Some of them I was able to answer while you're talking. We did get a couple more questions in here. We are running up against time, but if folks are interested, I'm okay staying on for a couple extra minutes. Mike, would you be available for a couple extra minutes?
Yes, sir.
So again, I was able to answer about half the questions. We've had 6 questions. I answered 3. So the ones I answered, somebody was interested in the photos that we used. So I will just say all the data, all the ortho imagery is available on POSDA, Pennsylvania Spatial Data Access, the 2012 and 15 ortho, and all the LiDAR data. All those data sets are available on POSDA. If you were specifically just looking for the images we used in the presentation, you can email either Mike or myself. I'd be happy to send you, just if you're just interested in the photos we used for this, I'm happy to do that. But if you just want to work with the data, it is accessible on POSDA. So a couple of questions that just came in late here. So given the 2 recession rates, which one will be used by local units of government to determine structure setbacks? That's from Kate Letterly. Kate, that's a great question. and definitely above our pay grade, Mike and I's pay grade. So the idea, the whole emphasis or genesis of this project was to see if we could develop an automated method for developing or assessing bluff coastal erosion. I think we can using high resolution LiDAR data and DISAS. So this report will be presented to DEP, but we will leave it up to the Coastal Resource Management Program and Pennsylvania DEP. If they want to use these data to address setbacks, that will be entirely up to them. We're happy to work with them, looking at the data, and we will obviously share the data with them. But as far as if this data will be used, it'll be really up to them. And one more question. Kate had a question prior to that. I'm not sure which areas were used in the photos, but for those areas of hive movement you showed, Mike,
Yes, sir.
do you know what the source of recession was there?
Dr. Foyle is also a geologist, and one of the phenomena he's been looking at is these areas of groundwater movement that happen, obviously below the surface. And it seems that they have what we call blowouts in certain types of soil and certain type of glacial material. And these areas seem to be the areas where we're having the largest, or have noted where the largest movement is. If I go back, I can, kind of show you. They also have an interesting kind of shape to them. So even looking at aerial photos and such, you notice the scallop kind of look to them. And then of course, sometimes it looks like rubble, but really in a lot of those places, if the homeowner hasn't done it, what you find there is glacial till and such. So the type of the soil and the glacial till that's in those areas, it seems that it gets held up by clay soils, so clay loves water to a point, and then it inhibits water movement or flow through it. So accumulating as it goes downhill, even though, we're inside the earth, gravity is still guiding that water and its movement towards the lake. And we think there's kind of a tie-in between these pockets of till, bigger rubble and rock and such in areas. And then behind them are kind of towards the lake surface areas where clays kind of build up and allow that water kind of to build pressure behind it. And then when we have thaws or we have big water events, big rains, or both of them together, we find that we're kind of really literally having blowouts, and they make the scallop surface. And I'll go back to that other one. You can kind of see it almost turns into a slurry in those areas where it's pushing things out. So, I'm not a geologist. Dr. Foyle would probably be a better person to give you even more specifics, and probably even journal articles or refereed articles out there that discuss this change on the surfaces. Other things, though, like I was saying before, humans kind of exacerbate the problem. So you can see different areas. If you were, say, to take a boat and just go along the shoreline from New York to Erie, where people have directed stormwater runoff right off of the face of the cliff, or they bury a black tube and it comes right out the surface there. And those areas, of course, are exacerbated, and we see big areas of movement in those areas as well. So those are two of the bigger reasons that I see. One being a natural phenomenon with the lacustrine and the also glacial type of soils that we have there, and how they build up in certain areas and create pockets of water and then have a surge that blows them out. And then, of course, humans kind of doing not the sustainable thing and directing, say, stormwater runoff right off of the face or into the face and then off to it below and such. Did that help?
Helped me. Hopefully it helped Kate. Yeah, and if you want to know a ton more about bluff recession, Tony Foyle's State of the Knowledge Report is an excellent resource. He also discussed a lot of the issues along our bluff on the past webinar, and so that's recorded and available on the Pennsylvania Sea Grant website, where he really went into some of the issues driving bluff recession in our area. So we have one more question that came in. So when is the next time the study will be done again? That's a good question. So we don't have any plans to do the study. Our goal here is to finish this up, wrap it up, get the report to DEP, have them review all these data, and then make a determination if this is something the state or the Commonwealth is interested in pursuing in the future. So I suspect if it does happen in the future, the data will just get better. I've already had preliminary discussions with the vendor, and where we were working with 0.7 meter density data in the last iteration, 2015, the last conversation I had with the vendor is, I mean, you can get upwards beyond 20 points per meter now. So just in 5 or 6 years, the LiDAR ability has significantly improved, and the costs have improved as well, where you can actually get better data. So I'll leave that question up to CZM. Another question here is, will this webinar be posted? Yes, this webinar has been recorded and will be posted on the Pennsylvania Sea Grant website. And then, so Kate has one more question. This is the last question we're going to take. I know I want to be respectful of everybody's time. I appreciate everybody staying on and participating. So Kate asked a great question, and one we've discussed a lot, Mike. I don't know if Tony's still on here as well. So the rates are less than the horizontal accuracy of the imagery. Are there concerns there?
I would say that that was an obvious concern of ours, and also of Woolpert's, and why we didn't use the earlier LiDAR data that we had. And of course, as the newer stuff comes in, I think it becomes much more trustworthy when we have more and more points that are landing on the bluff and coming back as a return to the sensor. That is just going to make our data better and make it more trustworthy as well, I think. So I think that's a great question. And I think technology is definitely providing the answer by giving us more confidence in the sensor itself, but also in the derivated data that we're getting out of it as well. So it's kind of like when I was a student doing my PhD, you know, we were working with 30 meter DEMs, and with our stuff here, we were doing sub meter DEMs and such with this LiDAR data. So stuff is definitely getting better, you know, working with something that is 90 foot in resolution to nowadays working with things that are sub foot or sub half meter and such. So yeah, it is an issue. It's a thought. It's definitely something that came through our minds and made us definitely disinclude certain data that was there, but just didn't have the accuracy that we wanted. So yes, ma'am.
Great. Well, great questions. I think we'll wrap up. I don't see any additional questions coming in. I appreciate everybody's attendance today and the questions. I thought they were really good questions. And it's interesting, it's questions we were thinking about as well, especially with positional accuracy. And again, Mike, that's one of those things that just gets better with the technology, I think. So again, thank you all for attending the session 2 of the Pennsylvania Sea Grant Bluff webinar series. Our next webinar will be held, let me cheat and look at my calendar, Friday, March 26th, and I will be your featured speaker that day. So I'll be talking about Walter website. So this is the Water and Land Technical Resources web center that we developed. So this is a website. So I will run you all through the website, what it features, and then specifically try to focus on some of the bluff resources that are available on that website. And again, if you have additional questions that come up, always feel free to reach out to Mike, Naber, or myself. We're happy to answer any questions you might have. And with that, I hope you all enjoy your weekends. Thank you for attending, everyone. And thank you, Mike.
Thank you, Sean. Thanks for the opportunity, Sarah.